Hello there, who speaks to you is Emil Valent, and today I'm going to discuss why discovering alien planets is a particularly bad starting point for sci-fi writers. So, if you didn't watch the show or did watch it a long time ago, keep in mind that I won't be showing footage of the show because I do not have time and patience for this much editing. So go watch the show. I'll come here for with a fresh mind. It's just 40ish minutes or so. So it isn't much of an effort. Done? Okay. So, Alien Planet is a show made by Discovery based off the book Expedition by Wayne Douglas Barlow. Now, Wayne Douglas Barlow is a pretty popular sci-fi writer, most known for is his work on speculative evolution and alien worlds. Now, Discovery's Alien Planet is a docufiction, not a documentary like some usually refer it to. Docufiction is a piece of fantasy and fiction pieced together in a scientific or accurate way, or journalistic way, if you wish. So it's like I want to tell a pretty cool story, but in a way that sounds real. Okay, it's basically that. Now, the problem with Discovery's Alien Planet was to try hard its way to the veracity of the point it makes, without actually doing anything about it. Okay. So it originated air on May 14, 2005, but it wasn't air as such type of work. You see, Discovery Channel has this perceived augmented credibility because it deals with science and nature science in general. So you see, it's produced by Discovery Channel. They must have put a lot of work and thought into it. Uh, Now, when you take a look at the production cast for Alien Planet, you see a lot of serious people. You see filmmakers, paleontologists, biologists, and chemists working into that. So when you dive deeper into the show to actually analyze, um, we start with a lot of statements saying, "Hey, we put a lot of work into this. We made a lot of research to make sure this is in line with the current scientific knowledge." Well, apart from not receiving the next Interstellar like I was waiting by this point, like 20 minutes into the show, I got pretty much disappointed with this. When we first get to the surface of the planet, meet the robotic probes and some microbes on the surface, we are then introduced to first animals. Okay, so this is the arrow tongue, and this is the gyro sprinter. So the arrow tongue is a predator, the gyro sprinter is a prey. Okay, they hunt down each other like in their natural habitat, sort of thing. Like Discovery usually does. Now I want to take a look at the gyro sprinter for a moment. So the gyro sprinter has 4 shoulders and 4 hips. The arms of the gyro sprinter are fused together into 1 foot. The same goes for its legs. Now I do not want to discuss how feasible this kind of locomotion is because I'm not an expert in that, but there's something I can and want to point out. Uh, how this came to be a viable solution in the first place. Like it descended for a four-legged animal, and its wrists and feet got fused together by evolution, by the process, and got into this pillar-like leg. But if you look at the mid stage, at the intermediary evolutionary stage for this kind of body plan, you see this is actually very inefficient. It's actually why we develop weapons that wrap around animals' feet so they cannot run from us when we hunt them. So I don't see why this came out to be a viable solution at all. I do not know. I don't have the slightest idea at which sequences this would be a viable solution that nature could come up with. When we look at nature on Earth and Celestial gets to its prey onto the same role, like the gazelle, we see horns as the defensive measures, and sexual display, of course. We see a slender body, muscular legs for agility and bursts of speed. Same with the cheetah, which is the predator of the gazelle. It has a muscular, slender body. Okay, its metabolism is able to cope with bursts of velocity of speed to catch up with the gazelle. Sometimes the gazelle stabs the cheetah, and sometimes it just uh, runs around and manages to escape to tire off the cheetah. Sometimes the cheetah is faster or smarter, or the gazelle didn't see the cheetah coming and it eventually dies. But the defensive and offensive mechanisms both of these creatures developed are pretty much in line with what would actually happen. Like if the prey is fast, the predator will develop a stronger body to cope with bursts of speed. If the prey is able to maneuver better, is able to make tight turns, well, the predator will be slender, more flexible, and able to stretch up to try and catch the prey. So you end up with a gazelle and cheetah. I'm not saying these two are developed to deal with each other perfectly. Of course, there's lots of variables that influence the development of the cheetah and the development of the gazelle, but it's not like they had to develop echolocation or fuse limbs or no, there are much more efficient ways, energy efficient, and that make evolutionary more sense than have fusing limbs or echolocation. So now let's take a look at uh, the arrow tongue. Okay, so like a lot of other creatures on Diving 4, the arrow tongue uses echolocation, okay, to locate its prey. So based off the behavior of ultrasound and sonar on the dry land, on the atmosphere, the the best effective range for the echolocation bubble of the arrow tongue is about 50 to 60 meters, so 5 to 6 body lengths in each direction, without counting shadows and interference, this sort of stuff. Okay. Now, on Diving 4, there's a clear difference between day and night. Okay. So it's not like the sea, where it's hard to see even during the day. You can pretty much see much farther during the day than during the night in Diving 4. Okay. So in the sea makes sense. Echolocation makes quite a sense because water has a thick optic depth, so you cannot see much further. Okay, it's not all that dark on the planet during the day. Like it's not like Saturn that only receives 1% light Earth does. Let's talk about eyes for a moment, okay? So the creatures of Diving 4, they have poorly developed eyes. They use echolocation, but they have eyes nonetheless. So on Earth, eyes appeared at the start of the complex life. Uh, uh, ab- when you take a look, at how recently echolocation appeared, it sounds quite like a joke. 52 million years ago, and with whales, 34 million years ago. So this is how much time eyes have been around before echolocation first appeared on the animal kingdom. You see, echolocation and heat sensing all appeared as auxiliary tools to vision and not as primary tools of sensing your environment. Uh, from the first moment prey develops eyes, the predator will develop some kind of vision, i.e. eyes as well. So the predator develops eyes, the prey develops better eyes, the predator develops even better eyes, and this cycle goes up. Okay, it's a self-feeding cycle. It's very much what inspires the light switch theory, which says that vision sparked the Cambrian explosion by changing how prey and predator interact in the environment. So you see, the arrow tongue has a range of 50 to 60 meters. Okay, so if the prey species develops eyes to see the arrow tongue from like 70 meters away, it's quite an advantage. When you have eyes, your distance, your view distance, is only limited by how tall you are and how thick the atmosphere is and how curved it's the horizon, which are minor details, but it's more noticeable of based on how tall you are. This is why when you take a look back at the gazelle has its head way above the ground while the cheetah tries to maintain a low profile. You see? So, we would eventually get to a point where the prey develops eyes, the arrow tongue develops better eyes, and the prey develops even better eyes, and so on and so forth, until all the creatures on level 4 on the food chain have some kind of proper visual system. Okay, let's get to the tree suckers then. So the tree suckers are brown with brightly colored stripes on their wings. Okay, they feed on the sap from the trees. Now I want you to take a look at the cicada and the moth. Okay, so the cicada feeds on sap from the trees, and the moth rests on the tree during the day before it can go on and fly during the night. They are camouflaged. They do not have brighter colors. So you could argue with me, hey, cicadas and moths can be brightly colored, and that's not an excuse for them to not exist. And say, yes, they can have bright colors, but they do have defensive mechanisms. Cicadas, they all sing at once, and when they perceive a predator nearby, they all shoot off at once so the predator cannot pinpoint the location of any one cicada. And when they are alone with the predator, they try to beat their wings in a menacing way to scare off the predator. The same goes for moths. The moths are colored in colors that usually mean, hey, do not mess with me, I represent danger, I'm poisonous, and something of the kind. So this extravagance is compensated by defense mechanisms. Whereas with the tree sucker, you just yank it out of the tree and stab to death without resisting or doing nothing about it. About the daggerists and these other creatures that hunt like wolves on the steppe, I'm not going to say much about them because they suffer from the same problems of the gyro sprinter. I'm not going to question why they behave like this. I'm going to question why this turned out to be a viable solution for their lifestyle. And then we get to the flying skewer. Okay, so the flying skewer is a particular case I actually got pretty interested in studying deeply. So the flying skewer is a flying creature, but it do not beat its wings to fly like a bird. No, it actually burns methane on these pods under its wings like a jet. So it's like a living plane. Using pixel measurements, I got to an approximate volume of 24.8 cubic meters. So let's make some estimates for the mass of the flying skewer based off this volume. Option A, 32.2 tons. Option B, 27.3 tons. Option C, 24.8 tons. And option D, 15 tons. I'm being pretty generous with this estimate. Trying to lowball it for as much as I can. But even so, the largest creature to ever fly over planet Earth was little more than 250 kilograms. That's quite a lot, but hey, the flying skewer has jets, literal jets, methane jets under its wings. So would it fly though? That's a question we are going to get deep about this. So the flying skewer burns methane. Okay, so methane has an exhaust velocity of 3.8 kilometers a second. To solve if the flying skewer would be able to produce enough thrust or have enough fuel to fly, we are going to use its velocity, its top speed. Okay, so I'm going to low its speed for half the top speed, so about 150 kilometers an hour, because well, it's not always going to fly at top speed, and we are going to ask ourselves if it can fly. Okay, so it can fly at a moderate velocity. Okay, let's use the rocket equation for this. So here there's a calculator. Okay, using the rocket equation. Okay, so here is the tox velocity, here's the initial mass, here's the final mass after the burn, and this is a conversion for kilometers an hour, from meters per second to kilometers an hour. Okay, so exhaust velocity 3,800 meters a second. Okay, dry mass of the animal 15 tons, and here we dial up the initial mass to 150 kilometers an hour, and to know how much fuel the creature would need. In this case, to get 150 kilometers an hour of delta V, we need about 165 kilograms of fuel to burn. Okay, here are the other parameters. For this, I'm considering how much time it would fly. I'm considering based off pixel measurements, how wide are the exhausts of the flying skewer. So I'm considering the exhausts of the flying skewer have a total diameter of 35 centimeters. Okay, 35 centimeters. So the flying skewer has 4 of these burners, so I'm going to count the nozzle of the exhaust times 4, because it has 4 of these burners. Here is the equation for thrust. Okay, thrust, burning 1 kilogram per second, making a difference in pressure of 1%. We get about 532 seconds of flight, which are equivalent to 8 minutes of flight, almost 9 minutes of flight. So let's round up to 9 minutes of flight. Okay, so for 9 minutes of flight, we need about 165.38 kilograms of fuel. Okay, so how much of this methane, how much of this fuel can the flying skewer extract from food? Well, if we consider the best case scenario, like the flying skewer feeds of fluids that are equivalent to cow dung in methane composition by weight, about 65% by weight methane, we arrive at the conclusion that the flying skewer would need to suck or eat or drink about 254.43 kilograms of fluids or raw material to extract this methane. Okay, so the flying squirrel is a 15-ton animal. It would technically just need to drink about 254 kilograms or liters of material. Sounds pretty reasonable, to be honest. But biodigestion is so painfully slow. 21 days. 21 days to produce 9 minutes of flight time. Imagine a flying squirrel grounded for 21 days before it can go to fly for 9 minutes. This is pretty much very inefficient, and even if it were like 4 times, 5 times as faster or efficient in producing methane, you still would need to be grounded for a week before going to fly for like 10-15 minutes at a time. It weighs too much and has poor fuel capacity and poor fuel storage and production. And then we get to the Emperor Sea Strider. Well, the Emperor Sea Strider, compared to other creatures, it eats through its feet. It's almost like a joke. Do I really need to say how that doesn't make any sense, even in the poor context, the poor phylogenetic context of Darwin Fall?